All right, so for this next section here, section 3.3, we're going to be continuing on with finding extremas of a function, except in this case, focusing on a closed interval of a given function of x. All right, so recall from the last section from 3.2, optimization to optimize a function means to find its maximum or minimum values. Optimizing a function means to find its maximum and or minimum values, like we did in the previous section with finding the relative extrema, like finding the relative max or the relative min. That is a form of optimization, optimizing a function. Now, what we did in the previous section, though, when we were trying to find the relative extrema, that was based on the entire domain of our function of x. We wanted to find the high points and the low points relative to the neighboring values around those extremas. But suppose we want to focus on just a closed interval, on just a little section of our function. Then in that case, if we're focusing on just a small piece of our graph, then what we want to look for is what's known as the absolute extrema. The underline's not working anymore. The absolute extrema values. Okay, and we have two of them, just like we did for the relative extrema. We have what's known as the absolute maximum value and the absolute minimum value. The absolute maximum value is the largest value of our function of x on its defined domain or some closed interval. Right, the defined domain will be the closed interval that we're focusing on. The absolute minimum, similarly, will be the smallest value on that defined domain. Now recall when we looked for relative extrema. When we look for the relative max or the relative min, it was possible that a function may have neither, that there might not be any relative extrema. When it comes to absolute extrema, since we're focusing on the biggest value and the smallest value, let me say value instead of values. So we're focusing on the biggest and smallest value within a defined domain. There always has to be a maximum and minimum value on that closed interval. So when finding absolute extrema, we should always have a maximum and a minimum, because we're looking for the biggest output. We're looking for the biggest y value on some defined closed interval. Okay, let me do a couple of graphical examples here. All right, suppose, say for example, suppose we have say an upwards parabola. But we know what an upwards parabola, that's an upwards arc. Draw that. And these type of graphs here, these are parabolas, if it's upwards, always has a minimum point, which is right at the vertex here. And that minimum, if we focus on this closed interval, that will be our absolute minimum value. Okay, but if we look at this piece of section, if we looked at this section here, let's see if we can draw this. If we looked at this part of our graph, and in that case, this point here will be the absolute minimum of this function within this interval from A to B. Okay, but let me just draw this in general for now. I suppose we had a downwards parabola. Now, if we have a downwards parabola, then in this case, we have a downwards arc. Does this one? Does not. And in that case, our minimum point would be the height of the, our maximum point would be the height of this arc. So that would be our absolute maximum if we were to define the entire domain of this function. But suppose we had a graph that had a bit of more curves to it. So let me draw another pair of axes here. And suppose we have graphs that say look like this. All right, and suppose we're looking at the interval. Let's say A to B. In that case, the absolute minimum will be the lowest point of this graph along this interval. And then the absolute maximum will be the highest point of this graph along this interval from A to B, which is pretty much going to be at these two critical points. So you're going to have our absolute minimum. And then here we'll have our absolute maximum value of that function. Okay. But suppose we had a graph to look like this. And suppose we didn't define our closed domain. Suppose we want to look at the entire domain. If we have a function that looks like this, and we don't define the domain that the interval, the domain that we want to focus on, then in this case, a graph just like this will have neither. Okay. If we were to define a closed domain, if we were to define a closed interval for this function, and we want to look for the absolute max or min, it will not exist because this goes towards positive infinity as we head along right to the x-axis, and this goes to negative infinity as we go to the left along the x-axis. But if we were to define a closed domain, in that case, an absolute max and min will exist. All right, so let me set up the steps here and how we go about finding these absolute extrema on a closed interval for a given function of x. All right, let's check zoom here. All right. Okay, so again, for this section, we're going to be looking at how to optimize a function on a closed interval. All right, so optimizing the function on a closed interval. I don't know why the underline is not working with this update. Something broke. So I'm just going to do this manually. All right, so to find the absolute extrema, the absolute max, and min for a continuous function on a closed interval, defined as A to B. All right, so closed brackets, we're looking at closed intervals, meaning we're including the endpoints as well, okay? If we want to find the absolute extrema here on the closed interval from A to B, the first step is to find all critical numbers on that closed interval. So find all critical numbers like we have done before of our function of x within this closed interval from A to B. All right, so just like within 3.1, find all the critical numbers. Except in this case, we don't have to do the first derivative tests. All we can do now after we find these critical numbers is evaluate our original function of x, not f prime, but the original function of x at these critical numbers, and also the endpoints, A and B, the endpoints that find on this closed interval. Okay, and then the largest value, or the largest and smallest values of our function of x here from the step 3 step two, from step two will be the absolute max and min respectively. Okay. So all we have to do here is find the critical numbers using the methods that we learned from 3.1. Then once we find those critical numbers, plug in what we found, plug in our critical numbers into the original function, but also plug in the lower and upper bound of our closed interval into that function as well. And the biggest output will be our absolute maximum, and the smallest output will be our absolute minimum. All right, let's do a couple of examples here. Let's find the absolute extrema of the following function of x. Where f of x, let's see, which one I want to do. Where f of x will be defined as x to the third minus 6x squared plus 9x plus 8. Now here we have a continuous polynomial function that is defined on all real numbers. And so the domain is all real numbers from negative infinity to positive infinity. But we want to find the absolute minimum maximum points of this function on the closed interval from -1 to 2. Okay, so this is the interval that we're focusing on, not the entire graph, but just this piece of it, where x is from -1 to 2. Okay, so first step, we need to find our critical numbers. And similarly to what we did in the beginning of this chapter, in chapter 3 here, to find these critical numbers, we got to define our first derivative, so f prime. All right, so the derivative of this function is going to be 3x squared minus 12x plus 9. And to recall what we do afterwards, set this function equal to 0. And what we're added here, let's see if there's any common factors we can pull out from these three terms. 3, -12, 9. These three coefficients have a common factor of 3. So let's pull out a 3 to the front, leaving us here on the inside with x squared minus 4x plus 3. All right, so now let's factor this quadratic out. So x squared minus 4x plus 3, that factors out into x, let's see, x minus 3 times x minus 1. Okay, and now set every factor that involves x equal to 0, solve for x. I'm going to be skipping some steps here since we've done plenty of these examples earlier in this chapter. So set x minus 3 to 0, x minus 1 equal to 0, solve for x to give us our critical numbers here of 1 and 3. All right, so here we have found two critical numbers for this cubic function at x equals 1 and x equals 3. But this part we also got to be careful with. Again, we want to find the absolute extrema. Oops, auto spell, change it to extreme. Extrema on the closed interval from -1 to 2. Again, we're not looking at the entire domain, just this defined domain. Look at our critical numbers. Our critical numbers are 1 and 3. Does 1 fall within this interval? Yes, right? 1 is between -1 and 2. But this 3 is 3 contained in this closed interval that we have defined? No, 3 falls outside of that interval. So in this case, since we're just looking at from -1 to 2, we don't have to worry about this second critical value, right? Because this critical value of 3 is not in our defined domain. Which, for our example, is from -1 to 2. Okay, so if we find a critical number that does not fall within our closed interval, then we don't have to worry about that critical value when it comes to the absolute extrema. All right, so now what's that's left is evaluate our function of x. We're going to evaluate f of x at the critical number that we have found that falls within our closed set, and also evaluate our function at these two endpoints of -1 and 2, where -1 is our lower bound of interest, I'll call that A, and 2 is our upper bound of interest, I'll call that B. All right, so let's first evaluate our critical numbers. So take our function, evaluate the critical number that we found, which is 1. So plugging in 1 into this original equation here, let's see, that's going to give us 1 minus 6 plus 9 plus 8, which gives us 12. So at 112. So when we plug in 1 to this function, it gives us an output of 12. Okay, but now we also got to evaluate our function at our endpoints, at the lower upper bound of our closed interval. So now we're going to plug in -1 to our function and +2 into our function. All right, so if we plug in -1 to this function, it's going to give us -1 minus 6 minus 9 plus 8, which gives us -8. So at -1, we get an output of -8 for this function. And now we plug in 2, our upper bound, our upper endpoint, into our original function. We get a value of 10. So 210. Okay, so now what we do is we look for the biggest y value of these 3 evaluations, and that will be our absolute maximum. So in this case, the biggest output was when x equals 1. So 112 is where we find our absolute maximum. Okay, and then to look at the absolute minimum, in this case would be at -8. -8 is the smallest output from the 3 evaluations. So -1 at -1, we get our absolute minimum here of -8. So our absolute minimum can be located at these coordinates. All right, so when x equals 1, we get an absolute maximum of 12. And when x equals -1, we get an absolute minimum of -8. All right. Let's do a couple more examples here. Okay. Let's do a couple more examples. Those are 2 more examples of finding these absolute extreme. Let's find the absolute extrema of a radical function. Let's find the absolute extrema of f of x, where f of x will be defined as the cube root of x squared. And we'll find the absolute extreme of this radical on the closed interval from -1 to 8. Okay, so again, first step, find our derivative. We got to find the critical numbers. So first step, once again, find the critical numbers. I'll use purple. So f prime of x. Well, let's see. Let's rewrite this function here. Cube root of x squared as the power function. We call it, when it comes to radical functions, we write them as power functions. So this will be the same thing as x to the 2/3 here. X to the 2/3, using the rules of exponents and radicals. All right, so the derivative of x to the 2/3, bring the power down, decrease the power by 1. That's going to give us 2/3 times x to the, that's 2/3 minus 1, gives us negative 1/3. All right. So now let's set this equal to 0. So 2/3, x of negative 1/3. Set this equal to 0. Let's rewrite this a bit. Let's make this negative power into a positive by flipping it. So this would be 2 over 3 times x to the 1/3 equal to 0. And recall from 3.1, our critical number is the value of x that either makes our function 0 or undefined. In this case, what will make this function undefined? If we get 0 in the denominator. How can we get 0 in the denominator? If x is equal to 0, right? If we plug in 0 for x, it's going to give us 3 times 0, which makes that function undefined. So here we have one critical number. So again, we set the numerator denominator equal to 0. In this case, 3x to the 1/3. Set this equal to 0, which gives us x equals 0 as our critical number. And 0 falls within our closed domain here. Okay. So now the second step, evaluation time. Let's evaluate our function of x at this critical number that we found, and also our two endpoints. So once again, we're going to plug in our critical number, which was 0, plug in our endpoints, which were negative 1 and 8, into the original function. Again, not the first derivative, the original function here. All right, so cube root of 0 squared, that's going to be cube root of 0, which is just 0. All right, cube root of negative 1 squared, negative 1 squared is positive 1, cube root of 1 is just 1. And then let's see here, cube root of 8 squared. 8 squared is 16. The cube root of 16 here, let's see, 2 times 2 times 2. Hold on, did I mess that up? Okay, cube root of 8 is 2. 2 squared would give us 4. All right. Cube root of 8 is 2. 2 squared gives us 4. Okay, so I'll set up the coordinates here. So here we have 0, 0. Here we have negative 1, 1. And then here we have, wait, 8 squared is 64. Cube root of 64 is 4. Yeah, that's correct. And then here we have 8, 4. Okay, now be careful on the homework. On the homework, they might ask for the coordinates, for the full coordinates, or they just might ask for the y values. So to look at our absolute maximum here, the absolute maximum is the biggest y value that we obtain from these evaluations, which in this case occurred at 4 here. So when x equals 8, y gives us 4, the biggest y value on this closed interval from negative 1 to 8. So 8, 4 is our absolute max. I'm going to say abs for absolute. And then the smallest y value would be our absolute minimum. And the smallest y value here is at 0. So 0, 0 would be our absolute minimum. All right. Let's do one last one here. One more. Let's find the absolute extrema of a rational function. Are we done polynomial? We've done the radical. Let's do a rational. In this case, a rational function f of x, defined as x over x squared plus 1 on the closed interval from negative 3 to 3. All right. So first step, find our critical numbers, which means we got to find the first derivative of this function. And how do we find the derivative of a rational again? When we have a function of x divided by another function of x, that calls for the quotient rule. All right, so let's define our functions here, f and g. F will be the top function, or so I'm already using f, so let me say h here. So h will be our top function, which is just x. G will be our bottom function, which is x squared plus 1. Find the derivative of each case, which gives us h prime at 1, and then g prime of 2x. All right, so now quotient rule time. So take the derivative of the numerator, which is just 1, multiply by the original function on the bottom of x squared plus 1, minus our original function on the top, which was just x, multiply by the derivative on the bottom, which was 2x, all over our derivative, our denominator squared, over x squared plus 1 squared. All right, so let's simplify this a bit. So we're gonna have, let's see, x squared plus 1 minus 2x squared over x squared plus 1 squared. Combine the like terms, we get our first derivative here of x squared minus 2x squared gives us negative x squared plus 1 over x squared plus 1 squared. All right, so now let's set this equal to 0 to find our critical values. X squared, negative x squared plus 1, negative x squared plus 1 over x squared plus 1 squared. Set equal to 0. And recall, to find the critical numbers of a rational, we set the numerator equal to 0 and our denominator equal to 0 and solve for each case, because again, we're trying to figure out what's going to make the function 0 and what's going to make the function undefined. Okay, so let's see here. So let's split this off into two equations. The first equation is negative x squared plus 1 equals 0. And for the denominator, let's just focus on the inside here, because whatever makes the inside 0, that number squared will still be 0. So x squared plus 1 equals 0. All right, so solving for x here, we have negative x squared equal negative 1, divide by negative 1 gives us x squared equal positive 1, and a square root in both sides gives us x equals plus or minus 1. Don't forget, when solving equations, when we square root, when we find an even root, we got to think of, when we take an even root here, we got to think of the positive and negative values. But now in this case, here we're going to have x squared equals negative 1. In other words, x equals square root of negative 1. Can we square root a negative number? No, because that's just going to give us two imaginary values at plus or minus I. So in this case, our two critical values are at plus and minus 1. Okay, so these two values we plug into this function will make it 0. So here we have our two critical numbers. So now let's take our two critical numbers of negative and positive 1, along with a closed interval here, our two endpoints, to find our absolute extrema. It keeps changing it to extreme. Okay. All right, so now that we have found our critical values, let's go to the second step. Let's evaluate our function of x. Okay, so let's evaluate our function at negative 1, at positive 1, the two critical numbers that we found from the previous step, and then our endpoints at negative 3 and positive 3. All right, so 4 evaluations we got to carry out here. And again, we're plugging these numbers into the original equation of x over x squared plus 1. Okay, not the derivative, the original equation. So plugging in -1 gives us an output of, let's see, 1 over 1 plus 1, 1/2. -1, oops, actually that would be -1/2 because the top will be negative. So -1/2. +1, let's see, 1 over 1 squared plus 1, 1 over 2. So 1/2 there as well. At -3 here, let's see, we're going to have -3 over -3 squared, which gives us 9. So -3 over 9 plus 1, which gives us -3/10. In the line for +3, we're going to get +3/10. Over 1, we can use a decimal, so it'd be 0.5. Oops, -0.5. Can't drop my negatives. -0.5, +0.5, -0.3, and +0.3. Okay, so in this case, the smallest value out of these 4 outputs is -0.5. So our absolute minimum is going to occur when x is -1 on this closed interval to give us an output of -0.5. All right, so 1 or -1, -0.5 gives our absolute minimum. And the biggest value out of these 4 valuations occurred when we got +0.5, which we get when x equals 1. So at 1.5, we'll find our absolute maximum point on this closed interval for this rational function. So in this case, our 2 critical numbers gave us our 2 absolute extrema. All right, so that is the basis here of finding the absolute extrema of a function, which is based on looking at a defined closed interval for a given function of x. So first step, we got to find the critical numbers using the methods that we learned from section 3.1. Then the second step, plug in those critical numbers into our function, and we only use the critical numbers that fall within our defined domain. And then evaluate our endpoints as well. And the biggest output would be our maximum, and the smallest output would be our minimum. And it is possible that 2 or more values of x here will give you the same max or the minimum. Okay, if that's the case, then those 2 points will be your max or minimum respectively. So like say if f of 3 gave us 0.5, then 3.5 and 1.5 will be our 2 absolute maximum. All right, so it is possible to have ties here. Okay, so let me pause this video for now and continue on the next other part here, looking at some more optimization problems, specifically for business applications.